Yeah, any questions before we begin? No? Okay, so let's do these. Here we go. We have a bunch of functions here. What's the derivative of this guy? What's f prime?
5x.
5x to the fourth, right? Real easy, right? When you have, now look at the difference between these. You have a function of x raised to a constant power, then that's just, we just use the power rule for that, right? The power drops down and you decrease the power by 1. Easy. Way different from having a constant raised to a function of x.
Yeah.
Right?
So that's just natural log of 5.
Yeah, right. And I can never remember this, right? And so what I do is I usually just say, okay, you know what? I'm going to do logarithmic differentiation. I'm going to take the log of both sides, like that. This gives me this. The whole reason I did that was so that the thing, the variable part, the function part, drops out, and now we get log 5, right? And so now we can take the derivative of both sides. Here, what's the derivative of log of something? 1 over the thing. And then we got to multiply by the derivative of the inside stuff, which is the thing that we're looking for. So that's nice that that popped out. Take the derivative of this. What's the derivative of that?
1 times what? Natural log of 5 plus...
Natural log of 5.
Plus 0.
Yeah. Or another way of thinking about that is log 5 is just a constant.
Yeah.
So that's just some constant times x.
Oh.
You take the derivative of that. It's just whatever that constant is, right? And so it just works out to be that. And so we bring this guy upstairs and we have g times log 5. G was originally 5x, or 5 to the x. So we have log 5, which is your constant, times 5 to the x. Okay, so just like you said, which is true, and if you know that, great. But I'm going somewhere with all this. Okay, so we got that. Now what about this guy? What do we do here?
3 times sine squared of x.
Right, so the 3 drops down, and then that gets decreased by 1, okay?
Times negative. Times cosine of x.
Times cosine, okay? Now, here's the thing, right? You have a function of x raised to a constant power, and you treat that just like this guy right here. That's a function of x raised to a constant power. So you do the same thing. You follow that same rule. The power rule applies. The only difference is now you have to multiply by the derivative of the inside stuff, right? But technically that is what you've done here, right? Like you have something raised to the 5th power, and so what you do is you say, okay, the 5 drops down, and then you decrease that, and then whatever's in there you multiply by the derivative of it, right? And so if that thing happens to be an x, what's the derivative of x with respect to x? It's just 1. So technically you have done that already.
Yeah.
It's just that we could kind of skip that step if that's what you're doing. So here we have a function of x that's not just x itself. And so we have to take that, we have to make sure that we are indeed explicitly taking that next step. And so we get 3 sine squared cosine. Okay? Everybody got that? Yeah. We're all comfortable with that? Now, here's like the worst case scenario. You have a function of x raised to a function of x. This power rule does not apply. The only time that you drop the thing down and decrease it is if the thing is being raised to a constant. This thing is not constant.
So,
what do we want to do? What do we do?
log of both sides.
Log of both sides, right? Because the problem in mathematics, whenever it's like, man, I have something locked up in an exponent, what could I do? Well, we know that our favorite property of logs is that it makes exponents drop down, right? And so if I do this, then now I no longer have that cosine locked up in an exponent. And so I could do this. And that is exactly what we want. So we want log k. Now I'm going to take the derivative of both sides.
So 1 over k.
1 over k times
Log And the derivative of k. So
the derivative of k, which is the thing we're looking for, right? Okay. Now what?
so it's
So I'm seeing
negative sine of x.
I'm seeing a product here, right? This thing times that thing. And so I'm going to take the derivative of this, which is just like you said, negative sine. So take the derivative of the first thing, leave the second thing alone. Add that to, leave the first thing alone, take the derivative of the second thing. What's the derivative of this part?
1 over sine of x times cosine of x.
Times the derivative of the inside stuff, which is cosine of x. And, I mean, we could call it cosine squared over sine, whatever, right?
Yeah.
And so let's get that real quick. Let's try to condense this. This is negative sine log sine. That's plus cos squared over sine.
Yeah.
And now that's over that. So why don't I bring him upstairs so we have k equals k prime. But that k was what we started with. So altogether we have, and I would probably write it like cosine squared over sine minus sine log sine. And then times that stuff, which is sine to the cosine. Okay. Right. Okay, but the thing I'm illustrating here is, when do you have to do this? Well, if you have a function of x raised to a function of x, or even if you have a constant raised to a function of x, this is all the case, right? Like, you could try to memorize some, try to get some general rule out of this. I think it's easier to just say, well, hold up. If I have a function of x up in an exponent, let's just take the log, and that'll make your life easier. And so, yeah, that's all I wanted to say on that. There's one other thing I want to talk about. Everybody got this? Everybody okay? I'm going to erase this. One other thing I want to talk about before we get into the meat and potatoes of the quiz. Here's a couple more things here. So, say we have f of x equals, I don't know, maybe x squared over, let's say, 3. And I want the derivative of it.
Well, it's just 1/3 times.
It's just
1/3 times 2x.
Times x squared, then you can...
1/3. No. The derivative. I'm not taking the antiderivative. I'm not going backwards. I want the derivative of this.
Yeah,
No,
it's
but it's the same
1/3
as
times.
Oh, 1/3. Okay,
And
so
then you can pull
yeah. Okay, so I'm sorry. Yes. You were saying this is just 1/3 times x squared, right?
Yeah.
And so so what's the derivative then?
2/3 x.
Right, because you could just say that's a constant. We take the derivative. It's the same thing as saying, well, the 2 drops down and you get that, and then whatever that constant is comes along for the ride. And so you would say, yeah, that's the same thing as 2/3 x right there. Now, why didn't we use the quotient rule?
It's hard.
It's harder. But it still works. It would still work. You could say, okay, quotient rule here, because we have something over something. So quotient rule. You take the derivative of the top thing, leave the bottom thing alone. Subtract off, leave the top thing alone, take the derivative of the bottom thing. What's the derivative of 3?
0.
Yeah. Now, we go over the thing squared. And that gives us 2 times 3 is 6x minus 0 is just that. Over 3 times 3, that's the same thing as 2 times 3 times x over 3 times 3. The 3's are gone, and I get 2x over 3. It'll work. You'll get there. It's just why, And it's real good to be able to, if you're given something, say, immediately identify what's constant here. What's constant? And can I get it all out to the front, right? Now, if your thing is a bit more complicated, like maybe root x over 7, like you can't pull it all out, but you could see this as, okay, my constant here, or maybe let's even make it a bit more funky here. Okay, you could say my constant here is just 1/3, and so you treat it like this. And you see my constant here is just 3/7 here. And you could just see it that, like, you don't need to rewrite it if you could just see it, but maybe it would be helpful to just rewrite it as, yeah, put your you get your constant out front, right? Okay, one more thing. Actually, two more things. Now, usually I shouldn't have to, well, if it's written like this, are A, B, C, or D variables?
No, they're constants.
No. Now, it would be different if I said something like this. There's a function of x and, say, D. And it's like, oh, D is something we could change and blah, 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 blah. But usually it's just like this. Now, if I just had something like this, I mean, if I did this, I would probably say that A, B, C, and D are all constants. They're all just constant real numbers. But usually that's what you do. Like if you have y's and x's, you assume x is the variable, y is the function or the output, and that everything else you see is just a constant. So let's do this one. Now do we need to use the quotient rule? Yeah, okay, so let's do that. What's the derivative of the top thing?
Just x. I mean, just a.
Just a, right? Because this thing, ax plus b, like if it were a 5x plus 2, you'd say, oh, okay, I know what that looks like. It looks like that, right? And you would just say, what's its slope? Well, it's in this case, if this were 5x plus 2, you'd say its slope is 5. Or you could plug it into it, and whatever. I mean, at this point, you should be able to say the derivative of this is 5. Yep. So therefore, the derivative of this is just a. Okay, so we have a times, leave the bottom thing alone, subtract off, leave the top thing alone, times just plain old c. Okay, and then the bottom thing gets squared. Okay, and that would be your thing. One thing I saw a couple times was the derivative of, say, this thing coming out to be a plus 1. Because in the head, you see, okay, there's my, I could take the derivative of that, that's just a. Take the derivative of that, well, it's just a it's a variable, you know, if you're thinking about b as a variable, and you say, you take the derivative of it, it becomes 1. But the function b itself, if I said f of x is just b, remember, that's just a constant. It goes through at b. And its slope is 0. Similarly, if b was 2, you wouldn't think twice about, well, when you take the derivative of it, it just goes to 0. But when you see b, you kind of get it in your head like, oh, I better take the derivative of it. It's, no. Constants go away when you take derivatives. Okay? Yeah. One last thing kind of on this, in this vein. Yeah, we'll do it this way. Say we have, I don't know, let's just leave it like that. Okay, actually, no, well, that's not, because I know what I would do in that case. I would just say, I'm trying not to make this too hard, but, okay. I'm gonna do it. Now, we could rearrange this. Pretend that we can't rearrange it. Like, you can, y squared goes up, the x squared, yeah, but pretend that it's not. Yeah, and let's say we want y prime. Yeah. Okay, and so this is an implicit differentiation problem. Your first question, the first problem is going to say find y prime by implicit differentiation. And you're going to have an expression with x's and y's, expression with x's and y's, etc. And this is what I want you to do. Now, okay, so let's just review. How do we do that over here?
That would be 1 times y plus x times y prime.
There you go, right? And what's happening here is we're kind of treating these both as functions. This is one way of thinking about it. And so you say, okay, if those are functions, I just use the product rule. We go x prime y plus x y prime. It just happens to be that we're taking the derivative with respect to x, so x prime goes away. It is equal to 1. And so you get y plus xy prime. use the quotient rule over here?
Yes.
Yeah, because we're treating y as a function of x. Now on the other hand, if I happen to say, okay, f of x is just x squared over y, and I just say y is just some number, it's just some constant. So I'm not going to do this to you. I'm just saying, like, if that were the case, then y would just be a constant. And you just say, well, okay, that's the same thing as this right here. And if I want its derivative, I would say then f prime is just 1 over y times 2x, which is just 2x over y. But that's not the game we're playing when we're doing this. In this case, y indeed is a function of x implicitly, or implicit. And so what do I do?
2x squared y minus
2x squared?
2xy.
2xy. So take the derivative of the top thing, leave the bottom thing alone. Then
minus x squared y prime.
do I add or subtract? Minus. Then what?
X squared times y prime.
X squared y prime over
y squared.
Y squared. And then we'd rearrange this, right? I'd probably bring him up, try to get all the y primes on one side, everybody else on the other side. You guys, I hope we've done enough of this that we don't need to go through and finish that. But there's the difference, right? And so, however, if it were xy equals x squared over 3, I wouldn't need to do that.
Yes.
We just take the derivative of this and say, okay, well that's just 2x over 3, right? We wouldn't need, and if you wanted to, you could go through and do the quotient rule over there. It just turns out that the derivative of 3 with respect to x is 0. And so, yeah. Okay, that's some stuff I wanted to clear up beforehand. So I already told you, I just told you, one of your questions is going to be find y prime by implicit differentiation. Okay. Another one going to look something like this. So I'm going to give you an object and I'm going to do it like this. It might look something like this. And how did I want to do this? I think I wanted it to be 1. And I want find equation of tangent line to this object and I gotta give you, and I'm gonna give you a point. First off, is 1, 1 indeed on this thing? Turns out, yeah, plug in a 1 and a 1, and is it still true? 1/2 plus 1 times 1 is 1, minus 1/2 is indeed 1. So yes, that is on there. Okay. Now, what do we do? What do we need? Wait, hold up. It's asking me, find the equation of the tangent line. So what am I looking for? What's my goal? I should have something that looks like
Y prime equals
y equals
mx plus
mx plus b. That's the kind of thing I'm looking. My goal is that in the end, I should have something that looks like this. In order to get that, what 2 bits of information do I need?
The intercept and the slope.
How do we find the slope?
y prime.
We need y prime at this point. How do I find y prime?
Derivative of both sides. Or
Yeah.
you can add one. Oh.
Yeah, and so if this weren't here, let's just pretend that wasn't there. I could get y by itself, right? I mean, then I'd have to take a square root, and hopefully I take the correct square root. This being 1, 1, I'm assuming I'll take the positive 1 and all that, but then I have to deal with taking the derivative of the square root of stuff, and maybe that's nice, maybe it's not, I don't know. But like you said, just take the derivative of both sides with respect to x. Treat y as a function of x. It's kind of like the same problem. It's an implicit differentiation problem. And when I do that, what happens? What's the derivative of this with respect to x?
It's just 2x. Wait.
Okay,
No,
so
it's just x.
Yeah, because again, we're treating it like this, right? That over 2 is just a constant, so we can pull them out. And so when we take the derivative of it, the 2 drops down, we get the x to the first power, the 2's cancel, and I'm left with an x. Now, what happens with xy?
X prime times y
So x prime y
X prime is just
x times y
plus xy prime. What's x prime?
1.
Okay, so I could rewrite this as y plus xy prime. Okay, now what do we get?
Minus y.
Okay, minus y.
Equals 0.
Oh, minus y times
Oh,
y
y.
prime.
Oh,
Aha!
yeah.
Be very careful of that because this is a y of x. And so we do the chain rule. We have to do the chain rule with this. And so the 2 drops down and we get the y of x to the first power times whatever the derivative of that stuff is. These are tricky because we just did this and oh, my y prime popped out. I'm good to go. Don't neglect that this y prime is also going to pop out. And that equals what?
0.
Are you sure? Do we need to do the chain rule on 1? Because 1 is 1 over 1.
Yeah.
And if we want, we could take its derivative and say, okay, the derivative of the top is 0 times the bottom. Minus, leave the top alone, take the derivative of the bottom over 1 squared. Oh, it's 0. Okay, cool. So, I'm not going to do the chain rule on that. It's just 0. Okay, now what do we want to do?
Get the y primes to the other side.
Okay, so do you want to keep y prime here or take them over
Take
here?
them both.
Let's take them both over. Okay, so we have x plus y staying put. Y prime minus xy prime.
Now,
Factor out the y prime. That leaves me some stuff that I'm not even going to bother to write because I'm just going to take them downstairs.
y minus
Okay.
x.
Y minus x. Okay, and so what's the derivative? How do I find the derivative?
Well, we
Plug
just
in
did.
0. Wait.
I plug in what?
No, plug in 1. And 1.
Oh, find the slope.
There you go, right? Because
So
I'm
plug in
finding
one.
the slope. At what point? At 1, 1. So I plug in 1 and 1, and I get 1 plus 1 over 1 minus 1 equals y prime.
Oh, not good.
Uh-oh. Uh-oh. What happened? Well, I'll tell you what happened. You have some object, and I gave you a bad point. Because what happened is you got division by 0. I'm not going to do this to you.
Oh, the tangent.
I'm not, it happened to be, yeah. And so, but this is good to know. If you ever do something like this and you go, how could this be? Well, that's what happened. Like if you do this with a circle and you find like, uh-oh, my derivative there is division by 0, well, something like this happened. But let's pretend it didn't, okay? Let's pretend you plugged in the stuff, and let's just pretend that we did all this work and this came out like that. Then, what do we do?
So it's
just
1.
1.
So then you.
It's just 1. Okay, so y prime is equal to 1.
So y equals x plus b, and then you just plug.
Y
in.
equals
Then
1x
1
plus b.
equals- Then plug in the
Yeah,
1.
1 equals 1 plus b, so
So
b
b
equals
is
0.
0.
So y equals x.
So b equals 0 and y equals x is how you would do it. There you go. Okay, so I threw a wrench in the gears. I'm not gonna do that here. I've checked it. It doesn't do anything funky like give you a division by 0. But I want you to see that that happens sometimes. And you go, what? My life's falling apart. I don't know how this could possibly be the case. Well, it just happens to be that the tangent line's vertical, and so if that were to happen, you could still write the equation of the tangent line.
But the slope is.
It just happens to be, and so let's just imagine, right, what just happened, we had some object where here at 1, 1, the tangent line was like that, and so it does something like this. That's the object we were just working on. And you'd say, well, if I know the tangent line's vertical, then that equation of that line is just x equals what?
1.
1.
There you go. There's the equation of the tangent line at that point.
Yeah.
Slope is 0 divided by 0.
Yeah, it's right, exactly. And so it's this is where you have to kind of come back and say, okay, we can't just plug everything into some equation. We have to use our brains. And if something like this happens, you get that your slope is infinite. Well, it just must be a vertical line there. Just like, if I say, and here's an ellipse, and I want the tangent line right here, you should expect that the tangent line is vertical there. And so it's no longer y equals mx plus b, it would be x equals some number. In this case, it's just that x equals 1. Okay. But I'm telling you, you don't need to worry about that on this quiz. Unless I just did something wrong. Then that happens, in which case you know what to do. Okay. So, related rates problems. Oh boy. There's a lot of different related rates problems you could study. I'm going to suggest that you study the type and you could look through your homework on this. I'm going to suggest that you study the type where you have, like, I don't know, 2 ships moving somewhere, right? And so you have one ship moving, he's starting here at some point, wherever, and he's moving in, say, this direction at some speed. And let's say that the speed is s for speed. He's going s miles per hour, heading due east. You have some other ship that maybe he starts here.
These are the hardest ones.
And I know these are some of the hardest ones. Like I said, you're going to need a lot of time for this bad boy. And let's say he's moving at s. What comes after s? How about t miles? Let's not use s and t. Let's say a miles per hour and b miles per hour north. Okay? And they're moving in straight lines at a constant speed, right? He's moving this one's moving due north. This one's moving due east. There's a lot of different ways we could do this, but let's say at some time in the future, let's call it t, right? At some time, we want to know, so at some time, maybe that this guy is over here. And maybe this guy's over here at this time. And we want to know at time t, so this guy's here at t, this guy's here at time t. We want to know how fast is the distance between the two changing. Yeah. And so what we've done, like the way we did this in class, was we said, okay, it would be nice if I had like an x. I could say that wherever this guy is, his position is x. Wherever this guy is, his position, we'll just call it y. And what I want is d here. So what equation did we use?
So x squared plus.
There you go. We said that x squared plus y squared is equal to d squared. Don't forget that square. If I had $1 for every time I forgot to do d squared over here, I'd have like $6. But anyway, right? Now there's a few different ways you could deal with this because what you want is d prime. So you could say, okay, how do I get d prime to pop out of here?
Implicit.
What? There you go, implicit. And so what do I need to do?
Derivative, let's say.
Okay, so derivative here gives me what?
2x plus times 2x plus wait. Yeah. 2x times
X prime. This is what will mess you up because all the implicit ones that you've done up until this point, it's always a function. Your y is a function of x. Now we're no longer functions of x here. These are all functions of time now. And so you could think about this as here's t, y of t, and you have a d of t. And so when you take the derivative, that bad boy needs to pop out. What is x prime, by the way?
So.
Well, wait a second. So hold on. Let's finish this up. I'm sorry. I'm jumping ahead here. So now, what's the derivative of this one?
2y times y.
2y, y prime. What's the derivative over here?
2d times
2d, d prime. That's the thing I'm after, because it's asking me, how is d changing? How fast is the distance changing? D prime, in other words, big D dt is what we're calling d prime, right? That's the thing I want, so I need to get it by itself, etc., etc. What's x prime in this case?
Wait, it would just be 0. Yeah, 0, right?
So you're telling me that x is so x is the position of the ship.
Yeah.
And you're telling, and so then x prime would be the what of the ship?
This.
The speed.
Yeah, right.
The speed of the ship.
Yeah.
So what's x prime?
A.
Right? Whatever a happens to be. If it's like 27 miles per hour, then you could replace this guy with a 27. But it happens to be a. Okay, so a, right? We're just doing this because it's on the board, right? I mean, you just imagine there's a number. Okay, so what's y prime?
B.
It would just be b, right? Whatever that speed happens to be. Okay, 2d times d prime. Now, a bunch of different ways we could do. Now, if I said at time t, you'd have to figure out where these guys are. There's a few different ways that you could do this. One way we could deal with all of this is if, for instance, we knew that he started, say, 100 miles west of some point, right? Like there's a port here, right? And this guy starts 100 miles west of the port. He would be at minus 100. And this guy starts maybe 20 miles north of the port. Then he would start here. And what we could do is just write actual functions, write an actual x of t. Because we know that when we start, we're at time 0, right? And so when he starts, so that would be like, you're thinking about x versus t here. Here's your x, there's your t. When he starts, he's at minus 100. And he moves at a constant speed of a. Well, then this thing right here would have a slope of what? A. T. Do we have an intercept? Negative 100. Okay. What about y of t? Can we do the same thing with y?
bt plus 20. Right?
Y of t. Yeah, so he starts, again, I'm just thinking, okay, here's, so I'm imagining now we kind of see this as the north axis, right? If he starts here at 20 and he's moving up just straight north, then at a speed of b, then this line has to be plus 20 and the speed has to be bt. Now, okay, hold up now. So there's a few different ways we could have gone with this problem. We have the implicit problem here. And now, once we know what t is, we could plug these in and find the actual value of x, right? And the actual value of y. Because if I told you it was 5 hours later, you could just plug in a 5, and you'd do all that. And then you'd say, x is at this point 5 hours later, right?
Yeah.
Right? Y is at whatever point 5 hours later. And you could do that. And I'm going to get rid of this. What you could have done at the very beginning, and I don't care which way you choose to do this, you could have said at the very beginning, well, I know what x of t is. X of t is just at minus 100, and so I take that and square it. This guy's just bt plus 20, so bt plus 20 squared equals my distance of t squared. You could also have said, well, I know this is a positive distance. I could take the square root of both sides. You don't have to, but we could, right? We could say, take the square root, and now we have this. My distance is that right there. Or we could keep it implicit over here. That's fine too. Now let's just do that real quick. Now let's just take the derivative here. Now what do we get?
So 2 times at minus 100 times a
Times a, good. And then
plus 2 times bt plus 20 times b.
times b equals?
2 times d of t times d prime of t.
Which is the thing I'm looking for, right? And if you knew what time, if I told you t equals t, you would just plug in your t and you'd have everything you need, right?
Yeah.
You'd be able to find that you'd have to find the distance, which is whatever the distance is between those 2 points. It's pretty simple. That distance in this case would just be the square root of those 2 points, right? Whatever squared plus whatever squared, right?
Yeah.
But it's just another way you could do it, or once you've found your stuff, but in general it's going to look like this, yeah? I would practice some of these problems. I would also, if I were you, I would practice, like, so all the problems, like I just said, right? I would have given you an A. I would have said A is 20 miles per hour. Or B, you know, that's what the book is going to do. And it's going to say B is 50 miles per hour. And it'll give you an actual time. See what happens if you could do it with, can you get it general like this? Like, what if you had given me, instead of A is 20, what if you given me A is 7? What if you said A is 500? What if blah, 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 blah? Well, you could just do it, and then at the very end, plug it in with all your A's and stuff like that. Yeah. These, you can see how hard these problems are when you don't start at the origin, right? Like, if there were just some way, it would be really nice. It would be really nice if, like, on a quiz, somebody just gave you, if they both started at the same point. It would be really cool if somebody did that and just gave you a problem where they both start at the same point, because that would make all of this so much easier. Moving on. But it would be really good.
Like
though.
red herring.
What's up?
Maybe it's like red herring. You're tricking us.
Or maybe I'm not. But it would be really good for you guys if you could get, just imagine, like any of those problems you do, if instead of being given an actual number, like 27 miles per hour, what if you weren't given an actual number? What would you do in that case? Would you be able to come to the solution? Okay, so differential equations. You guys remember what a differential equation is? There's so much on this quiz. This is why I'm giving you forever to do this.
It's just a slope at a given.
A differential equation is any equation that involves derivatives.
Yeah.
Right? And so, like if I said y prime equals y, that's a differential equation. So it says that we're looking for a function where we want a y of t, say, that has this property.
Yeah.
What function has this property? It's equal to its own derivative.
Slope.
E.
E.
Oh yeah.
E to the x.
So would it be e to the
E to the x. E to the y.
e to the
Wait.
E to the t.
e to the t, right? Okay. And usually with differential equations, t is the input variable. I don't know why. That's just what they did, right? But I mean, oftentimes you see it without, but it's just usually when you see something like this, you'll give your answer in terms of t. But okay, so now I claim that this is a solution. How could we check that this is a solution to that differential equation?
Take the log of that.
I take the what?
The derivative of both sides there. So that it's be y prime of t equals e to the t.
And then I plug it in and just
Yeah.
see, does it work? Yeah, it does.
Yeah.
Okay. Now, the types of problems you had in your book were something like this. They'll say, this is a differential equation. Show that this is a differential equation. Show that this is a solution to the differential equation.
Okay.
What do you need to do?
Second derivative of that.
Okay, so what do I need
You
to
need
do?
to take the first derivative.
Take the first derivative, which is what?
E to the 2t times 2.
Times 2.
And then take the second, which is
E to the 2t times 4.
Yeah, so 2 times the derivative of e to the 2t, which is e to the 2t times 2,
4 times.
which is 4 e to the 2t, yeah.
Plug up into
And now I plug it in, right? And I say, okay, let's check that this solves it. This goes here, so 4e to the 2t minus 4 times the y is e to the 2t, and I get 0.
Yeah.
And so, okay, good. So it is a solution to the differential equation. But suppose I gave you something like this. And suppose I told you the function y of t equals e to the rt is a solution to this differential equation for exactly 2 values of r.
Oh, and find out.
Deduce what these values are by, and I'm even going to be nice, by taking derivatives of the given function, plugging them into the differential equation, and manipulating the result so that an Algebra 2 student can understand your argument. Okay, so what are we going to do?
Take the derivative of both sides of the
Okay, so that gives us what?
y prime equals
Y prime equals,
r to
that's an R, yeah, R,
e to the rt.
e to the RT. Now what?
Plug it in. Oh wait, no, take the second.
Yeah, it's not there yet, so we got to get the second derivative, which is what?
R squared e to the rt.
Yep, R squared e to the RT. Now what do you want to do? I mean, I just told you what to do. Plug it in, right? Okay, so y double prime is R squared e to the RT minus 4 times what?
E to the rt.
4 times what?
E to the rt.
E to the RT equals 0. Now what do you do? We're trying to
just need
find the
R.
values of R. So what now?
We need r, so well, we need to take a log of this stuff. Yeah. No, that one.
So I'm going to help you.
Oh, add the 4e and then divide by. Add to the 4e to the rt and then just divide by.
Yeah, you could, and that's okay. So you're saying bring this guy over there and then divide by that. But what if this were more complicated? What if this were like r to the 4th e to the rt plus 7r cubed e to the rt minus, I don't know, 100 over pi e to the rt plus a bunch of things plus a happy face e to the rt equals 0. What would you do in this case?
Take the derivative of both sides.
Yeah. And that's going to make your life much worse.
Factor
Factor out an e to the RT.
Oh.
And why? So let's look at this, right?
Well, let's face
We're
it.
trying to solve, there's some equation equal to 0. And this goes right back to like anything we've ever done, right? So if you have 100x minus 50 equals 0. Yeah, okay, yes, you could bring the 0 over. But it's just like, if you have common things here, and you could factor something out, you have 2x minus 1 and 50 out front, now you could get rid of that 50. And you can pretty much just say, and just look at this and say, okay, when is that guy equal to 0? And that makes your life much easier, right?
Yeah.
Same kind of thing here. It's like, you're saying, well, take the log, maybe move it over and take the log. It's like, that's not going to help you at all. The cool thing about e to any power is that it's always non-zero. Is e to anything ever 0? This could be e to the 700 times root 3x, and it's never equal to 0. It could be negative 700 to the root 3x, and it looks like this. Doesn't matter what that r is. That's never 0. So can we divide by it? Yeah. Or you could just say, hey, look, I got some constant and some thing there. So now, what do you do there?
It's just r plus 2
Plus
or
or
minus
minus
2.
2.
Yeah, I mean, we could factor it, or you could say, this will be true whenever r squared minus 4 is equal to 0. Just like any time we've worked with anything, and you have an x minus 2, x plus 5, x minus 7 equals 0, and you could have any constant out front, right? Like 70. You don't even look at that. You just say, okay, I just need to make that 0, make that 0, make that 0. It's the same kind of thing here. And once you got that guy to be 0, which happens when this happens, which happens when this happens, which happens plus or minus 2, then you can answer my question. And this is what I mean by getting it into a form where an Algebra 2 student can then understand your argument. You're saying, this equals 0 whenever that's true. And that, and therefore, y of t equals e to the rt works whenever r is equal to plus or minus 2. That will solve the original differential equation.
Yeah.
Right? Okay. A little bit more. Well, a lot of bit more on your quiz. We already talked about that. Good luck with that one. Boy. Okay, now maxima and minima. Okay? So, know the
Chapter
difference.
4, right?
Say again?
The stuff from chapter 4.
Yes. Now we're back into chapter 4 stuff, right? Like, know the difference between, well, now I want to find the absolute max and absolute min on, let's say, 0 to 5. What's the absolute max and the absolute min of this? What do I need to do?
Derivative.
Yeah.
And so,
Okay. Which is what? What's the derivative?
2x minus 2.
Which is, and then
Equals
now I want to
0.
set that equal. I want to set that equal to 0.
X equals 1.
When x equals 1, do you have a max or a min, or what's going on?
We'll take the second derivative and then see if it's
Yeah, that's good. That's really good. And I will tell you explicitly in a different question to tell me I say use the second derivative test to tell me which one of these is a min and which one is a max. So let's do that right here. So take the second derivative,
It's just
2.
which means that f is what? Concave
Upward. Concave.
concave.
up. Okay, so x is concave up
So it's a min.
at this point. So this must be a min. But I'm asking you, is this an absolute min or max? And I'm telling you, find both the absolute min and the absolute max on this closed interval. How can we be sure? So what do we do? What else do we have to do?
Plug in
Plug in what?
0 and a 5.
Yeah, because this is what's going on here, right?
Oh, right, yeah.
Okay, it looks like we have here at 1, I have no idea what this thing looks like. It might look like this. So here's 1. Here's what it is at 0. It goes up at 7. Now, over here at 5 is probably the the max. And maybe that's a min. But again, and like if this were more complicated, if that were like to the 5th power minus something to the 3rd power plus blah, 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 I wouldn't know. But what I could tell you is if we check all the maxes and mins, right, all of the local maxima and minima, and all of the end points, then we'd be able to find it, right? So you had a bunch of problems like this. And so that's what you'll have to do. And so let's just do that. We plug in a 1 and we get f of 1 is 1 minus 2 plus 7 is
6.
6. Now plug in a 0. F of 0 we get 7. Now what else do we have to plug in? F of 5, which is 5 squared minus 10 plus 7. 25 minus 10 plus 7. Did you say 23?
Yeah.
I'll buy that. 23. So which is my absolute?
22.
No, okay, I don't care. It's some number. Okay, yes, it does matter. Okay, so which is the absolute max and which is the absolute min on this interval?
22 says. F of
This
5.
is, so there you go. And that's what I would like to see. So I would say the absolute max is at 5 and you get out of 22. And what's the absolute min?
F of 2.
F of
Oh, f of
1 equals 2.
Yeah, it did get it to us, right?
6.
F of 1 equals 6. Here's the picture, which you're not going to draw. You're not going to draw that guy, right? I mean, the picture, I can tell you the one that I'm giving you, you're not going to waste your time trying to draw it. But this is what you'd have to do if I tell you to find the absolute max and min on a closed interval.
And then
On an open interval, you don't need to check the endpoints. I mean, and on an open, if I were to give you an open interval, I probably wouldn't use the words absolute max and min. In fact, I'd probably just tell you what's going on. And I did tell you what's going on. It's a little different. But I mean, you need to know, if you want to find the absolute max and min on a closed interval, you got to check the endpoints. your notes about that. There's a theorem. I think it was. Whatever. Who cares? It's there's a theorem about that. We talked about it. It's just yeah. We talked about it at length. Okay. Finally. I'm gonna give you something. Okay, we got enough time. So, of course. Let's do it this way. Now, how do you find all... Clearly there's no absolute max and min for this guy. He's a cubic, right? So he's going to do this forever and he's going to do this forever. So I'm not going to bother to ask you about absolute max and mins. But it's possible that there are local maxes and mins, right? So how do you find... How do I word it? How do you find all local maxima and minima?
Derivative equals 0.
Alright, then we take the derivative,
3x.
which is what? There you go. Okay,
3x
what?
squared minus 2x plus 1
And I do what with it?
equals 0.
Set it equal to 0.
We can factor
Can I factor it?
We'll find that.
Let's find
3x
that.
times x.
3 and that.
Minus...
A 1 and a 1. It has to be, right? And then
We
what?
want minus 1 on the right.
Minus 1 over here.
Yeah, and then plus.
And a plus
no,
1.
Another...
Yeah, that's right.
Yeah. No, that doesn't
Oh,
go.
they both
You
need to be
two
minuses.
minuses. Wait,
We
but that,
need 2 minuses. There we go.
that won't work though.
Oh no! So what do we have to do?
Quadratic.
There you go. Okay, so let's do our quadratic, and that gives me x equals 2 plus or minus 4 minus 4 times a times c, which is 4 times 3. We get a complex number. Okay, whatever. Let's pretend that we didn't get a complex number. Let's do it.
Now we
this
can
way.
factor.
All right, now let's do it.
So it's
It's 3x plus 1 times x minus
yeah.
x equals what? Negative 1/3. And
There you go. Okay, so x equals negative 1/3 and x equals
1.
1. Okay, now which one's a min and which one's a max? And how do we find out?
Oh, you can hit the second derivative.
Yeah, and I'll tell you explicitly to use the second derivative test to tell me which one is which. So let's take the second derivative.
So
6x minus 2.
Okay, so
plug in those points and see.
plug in the point. So f double prime of negative 1/3 is equal to 3 negative 1/3
Wait, no, you plug it
squared.
Plug it into the 6.
Thank you.
So then
Much easier. Thank you.
So negative
Negative 2.
or 2
Negative 2
minus 2.
minus
So
2
it's negative, so
is
it's
negative
concave
4.
down, which is a max.
Concave. There you go. Okay, so we would say from here we could say concave down. Therefore, max at x equals minus 1/3. But what's the value?
Plug it into the
F.
top one.
Yeah.
Plug it into the top one. So we have x of minus 1/3 equals whatever it is. Okay. Now what you could do is like you could just plug both of them in and say, well, that one's bigger than that one, so that one has to be a max. But that technically does not tell us whether or not it is a min or a max. Because what if it happened to be something like this? Right? You would get that, oh, it's less than that, but is it a max? We don't know unless that guy's actually less than 0, right? If the second derivative is equal to 0, you might end up with what's called a saddle point right there. You don't want that, right? You need to be able to tell, all right? So what about the other one? That's why I'm telling you explicitly to use the second derivative test. So the second derivative here at 1 is equal to 6 times 1 minus 2 is 6 minus 2 is positive 4. So it's bigger than 0, so it's concave.
Yeah.
So it's
Up.
min.
And so it must be a min at f of 1 equals whatever it is. Okay? It's not enough to just plug it back in and see which one's bigger, because without the second derivative test, you don't know whether or not it is a max or a min. If the second derivative came out to be 0, right, like if this had worked out to plus 2 minus 2 equals 0, then we wouldn't have any information. We wouldn't be able to tell, right? Okay? So, okay, we have enough information on here to do the other thing that I'm going to ask you to do, which is find the intervals on which f is increasing. Where is f increasing?
So
F is increasing when
the derivative is positive. So
the derivative is positive. And f is decreasing when
the derivative is negative.
the derivative is negative. So where's the derivative positive? Where's the derivative negative?
So
How would you go about doing this?
Can plug in a point on
Good. Okay, go plug it. How many points would you like to plug in? Because there are infinitely many in every interval.
Well, it's at 0 at negative 1/3.
Okay.
And so then it does this. So
Hey, so you're kind of what you're doing here is you're kind of telling me, like, graphically, that there's something going on here. It'd be much easier if I had $1 for every student who refused to graph things. I have way more than $6. It's like your life would be much easier if you just graph it. So let's graph f prime here. We could graph f prime. We know, so it's what type of object is this?
a parabola.
It's a parabola. Does it open up or does it open down? So it's concave up.
Yeah.
Okay? And we happen to know where its two zeros are. And so we could say it looks like this. So now, where is f increase? Oh, and by the way, this is at minus 1/3. This is at 1. So, where is f increasing on?
So negative infinity to negative.
Yeah.
Oh,
to negative 1/3.
third, and then for union with 1 to
Then negative 1 to infinity. And then
1
decreasing on
And f is decreasing.
negative 1/3 to 1.
There you go.
Yeah.
Isn't this much easier?
Yeah.
I've had
That's a lot
students who are like, well, like they'll do this. We want to know where the derivative is positive. Good luck.
Yeah.
Good luck doing this analytically. Good luck manipulating this around. Because what you end up getting is this. You're after like failing about 7 times, you go, okay, this is probably my best guess. And then you have to say, okay, well, if one's positive and one's negative, then that's not true. So where are they both negative or where are they both positive? It happens to be out here is where they're both negative and where they're both positive. You could have just graphed it.
Yeah,
You
that's-
could have just graphed it. Now, last question. Okay, so on one hand, the answer to half the questions is take the derivative and set it equal to 0. The other half of the questions are just graph it. Just graph it. So here's my final question. F is concave up. Where? Whenever
F double
F,
prime of x is positive. So
Yeah.
and F is concave down
When it's negative.
when F double prime is negative. So my question is, find the intervals on which F is concave down. Where is F concave down?
We'll graph it.
Hmm?
If we graph.
Let's grab it. Let's grab it, right? -2, positive slope. Boy, we could answer this real easy if we knew what point that was. What point is that?
Like
1.
we're gonna have -2.
Wait.
Wait, no, we can't. -2 equals 6x.
And
minus 2,
1/3,
and then
right?
solve for x.
6x minus 2 equals
6
0.
x minus 2 is equal to
negative
0.
So it's
2/3.
1/3.
6x equals
Is it
2.
2/3?
X
One-third.
is
1/3.
2 6's 1/3. Okay, so there's 1/3. In other words, graph it. Graph it. You know, back in Algebra 2, I said anytime you draw something and something crosses an axis, just go ahead and find where it crosses the axis. Like, that was a rule in Algebra 2. I was like, if you ever turn something into me and you draw something that crosses an axis, even if I haven't asked you about it, just write where it crosses the axis.
Yeah.
Because from now on, always write where it crosses the axis. You should be at a point now, I mean, if you have been listening to me for the last 2.5 years, then this should be rote for you. You start drawing something, you're like, all right, what does this thing look like? Oh, I better find that point. So it's just rote. You just go, oh, let me just set that equal to 0. Now you can answer all these questions. So where is f concave down?
From -infinity to 1/3.
Up to where?
1/3.
Up to 1/3.
Including or excluding?
Exclude.
Excluding, because we don't know what's happening to actually what we do. But, okay, f is concave up.
1/3
1/3.
infinity.
1/3
No,
to
it was-
infinity. There we go. So there you go.
What about the inflection? That's just at 1/3.
It would be at 1/3.
It would, the inflection point where it changes concavity is the inflection point, right? And if I were to ask you about that, then I would ask you about that. Where is its inflection point? Now, here's a question. Let's say, so forget, okay, everybody got all this? So here's a quick question. Let's say I know nothing about f. All I know is that f double prime, the second derivative of f, looks like this.
Yeah. So, then drop the first derivative pretty easy.
Well, it's just, now, but here's the question. So all I know is this. So where does, so question number 1, yes or no, just yes or no, does f have any inflection points?
Yes.
Where?
1,
-1
and 1.
1 and 3.
3.
Inflection points at where?
-1 1 and 3.
I disagree. So here's a question. Okay, here's another question. Here's another question.
Not
Where? Watch this.
Oh, because
watch. Ah, ha, 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 ha. Where f
Oh.
is concave up? Where? Where is f concave up?
-1
to 1.
to
-1 to
no,
where?
to the vertex of it. Wait,
To 3. Oh, to
Whoa,
1.
whoa, 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 whoa! This is f double prime. I'm not.
only to,
-1
Concave
to
up.
3.
When is so? F is concave up when what?
It's positive, so -1.
When its second derivative is strictly bigger than
Oh, so
0.
not including 1. So,
So
-1
no.
to 3, not including 1.
Yeah. So in other words, like
Oh.
this. Yeah. Now where is f concave down?
-infinity to 1 and 3 to infinity. -infinity to -1.
Yeah, -1. Thank you. And then 3 to infinity. Now an inflection point is where concavity switches from one to the other. And so here we're concave down. It switches to concave up.
Yeah.
So that is an inflection point. Here we're concave up. We stop, but we're concave up again.
Yeah.
So did it switch concavity?
No, it did the.
No, so we
South.
don't have, yeah, we don't have an inflection point here. Now that we're over here, are we concave up or concave down?
yeah. So it is there is one at 3 and
And so, say again?
there's an inflection point at 3.
There is an
And
inflection
negative
point,
one.
yeah. So we have inflection points wherever concavity switches. Concavity switches when we cross from one to the other. And so the inflection points would be at -1 and at 3, but not here. This is why the second derivative test fails if it's actually equal to 0 there. So let's say we had some function that did this, right? And we wanted to know and it happened to be the case that f prime at 1 worked out to be 0. And I were to ask, is that a min or a max? You'd say, well, its derivative is 0. It's neither concave up nor concave down. It's not switching from concave up to concave down. In fact, it was concave up, and now it's concave up again, right? Yeah, so that's not, I mean, it's probably doing something like, oh, I can't even draw, I don't know how to do that. We'd have to take some derivative, we'd have to take some anti-derivatives and figure out what this thing looks like. But at any rate, so inflection points occur where concavity switches from up to down. So you can guarantee that's one. But second derivative test doesn't tell you anything about this, right? Okay. Any questions before we go? That covers everything that's on the quiz. Then you have an extra credit problem, which has something to do with this type of stuff. It's not too hard. That one's not. I normally make those the tricky one that I was going to make extra credit is just one of your regular problems. Good luck with that. But if you've been paying attention, especially to what we did today, you should be able to get it. Yeah. If while you guys are taking this, I don't know, you really shouldn't have any questions. This should be really, I mean, it's, like I said, I could have made this really bad, but I said I would kind of explain. Each of the things that I've asked you to do, I've told you what I'm going to ask you to do. Each of those functions or whatever I've given you could have been much worse. I tried to keep those easy. It's just if you understand all the stuff we've done today, there shouldn't be any problems about this, except for problem 3 and problem 4. Problem 5's really bad. So problem 3, 4, and 5 might have some problems, but
Okay.
you might want to go back over this video and just listen to it again, because I've dropped a bunch of hints.
Okay.
I've dropped a bunch of hints. Actually,
Today, yeah.
yeah. I'll get this going as soon as possible. Oh, 4's not bad. I gave you 4. Never mind. 4 is simple. 5 is, you get 5. I'll be generous with grading 5. But
Okay. Was that the one that was going to be the extra credit?
Yeah. Yeah.
Alright.
All right, guys. Good luck. Merry Christmas.
Yeah, I guess.